Now the question is, can we generalize all the concepts that we've learned so far to spaces that are more general than R? And yes, we can, and this is precisely the concept of a metric space. So let me remind you of the important properties we needed for absolute values. Well, there were three of them. First of all, absolute value of x minus y is always non-negative, and the only way it's 0 is if and only if x equals y. And second of all, the distance between x minus y equals the distance between y and x. And last but not least, the single most important inequality of them all, which is the triangle inequality, which just says x minus z is less than or equal to x minus y plus y minus z. And what this means, at least geometrically, is if you have a triangle with vertices x, y, and z, then the length of the third leg is less than or equal to the sum of the lengths of the other two legs. Now, what's the idea behind a metric space? Let's forget everything we know about R except for those three properties. And that's what you get is what's called a metric space. So definition, SD is a metric space. So if one a set S with what's called a distance function D is a metric space if and only if the following things hold. First of all, and you'd be surprised how similar it is. So the distance between x and y, it's greater or equal to 0. And the only way it's 0 is if and only if x equals y. And the distance between x and y equals to the distance between y and x. And last but not least, the triangle inequality. So the distance between x and z, it's less than or equal to the distance between x and y plus the distance between y and z. Okay, and the nice thing is, because this definition is so general, a lot of things are metric spaces. So for instance, you could have the real numbers, of course, with the absolute value, but of course RK with the usual distance function, but also the rational numbers with absolute value, and any non-empty set with what's called the discrete metric, which is a very funky kind of metric, but then also sequences and continuous functions as well. So really a lot of things are metric spaces, so we'll be able to say a lot of things about a lot of things. And in particular, we can easily generalize the notion of convergence. So if you remember, what is the notion of convergence in R? Well, Sn converges to S if for all epsilon. So no matter how small the error is, there is a threshold, capital N, such that if n is bigger than capital N, then the distance between Sn and S is less than epsilon. So that was for the real numbers. And again, what this means is that no matter how small the error, you can always find a very large threshold, capital N, such that after this threshold, Sn is at most epsilon away from S. So again, no matter how small the error, Sn is eventually in that region of radius epsilon. All right, but here's the nice thing. The only thing about absolute value here that we use is a distance. So in fact, the general definition for metric spaces is just the same thing, except you replace absolute value with the distance. So such that for large n, the distance between Sn and S is less than epsilon. How cool is that? And another notion that was important was the notion of a Cauchy sequence, which is the same thing, except this time we're saying Sn and Sm are close to each other instead of being close to a fixed number. So definition, Sn is Cauchy if for all epsilon there is some threshold capital N such that after this threshold, so if m and n are bigger than capital N, then Sm and Sn are close to each other. And the question is Cauchy the same thing as convergence? Ness, again, because it depends on your space, and in particular, if your space is complete, if Cauchy implies convergence, then your space is complete. S is complete if any Cauchy sequence converges. So if Cauchy implies convergence. Okay. So for instance, the rational numbers turns out are not complete, but the real numbers are complete, which is again what makes the real numbers so much better. But also r to the k is also complete. And I believe from that we can deduce the Bolzano-Weierstrass theorem for r to the k. Now, another notion that was useful in the real numbers was the notion of an open interval, or more generally an open ball. So Bxr is just a set of points that are a distance at most r away from this point x. And with this, we can define the notion of an open set. And basically, E is open if, no matter which point in E you have some wiggle room. In other words, you can always squeeze a little ball around x that's still in E. So definition, E is open if for all x in E, you can find a tiny radius, so there is r positive with the ball Bxr is included in E. So no matter which point you're at, you can always squeeze a very tiny ball in that set. And interestingly related to this concept is the concept of an open set. And this one has to do with limits of sequences. So first of all, definition, we say that a number S or an element S is in E bar if you can find a sequence in E converging to it. So this is what's called a limit point. It's the set of all the limits of the sequence of points in E. So in other words, definition, S is in E bar if you can find, so if there is a sequence Sn in E with Sn converging to S. In other words, it's the limit point of some sequence in E. And more precisely, E is closed if it contains all the limit points. So you cannot escape this set by taking limits. So in general you can, but not in closed sets. So definition, E is closed if E bar equals E. All right, last thing, one more thing that was useful about at least closed balls is the following. Well, notice closed balls, they're closed, of course, and also bounded. And the question is, can you generalize the notion of closed and bounded sets? And yes, it's called compactness, which I cannot really explain in detail in 2 minutes, but essentially, all that a compact set is that you can, no matter how big your cover is, so no matter how you cover it with open patches, you never need infinitely many of the patches. In other words, definition, E is compact. Okay. If every open cover of E has a finite subcover. And the nice thing is we can show that if E is compact, then it's closed and bounded. Okay. But the beautiful thing is in R to the K, and that's called the Heine-Borel theorem, the converse is also true, which gives us a complete characterization of compact sets. And lastly, there's a really nice example of a compact set called the Cantor set, which at each point, you start with the interval 0, 1, and at each point, you just remove the middle third of it, and at the end, you get this dusty kind of thing. And it turns out this Cantor set, it's also compact. So it's a nice example of a compact set. All right, thank you.